Meredith Rawls. I'm a postdoc here at the University of Washington in the Department of Astronomy, and I work with the Large Synoptic Survey Telescope data management team, and I'm also a DiRAC fellow. The Large Synoptic Survey Telescope, or LSST, is going to make the highest resolution movie of the night sky ever made, and it's going to do it over a decade. So it's going to be a really awesome opportunity to learn about lots of different areas of astrophysics. But one key thing that we also have to do to even let this happen at all is write really good software to handle all the images that it's taking. So if you can imagine this big telescope, it's under construction right now in Chile, and I'm really excited because it's starting to look like the renderings that we see. And it is going to take something like 20 terabytes of data every single night. Images. It has a 3.2 gigapixel camera. That's like hundreds of iPhones. And every single night, 20 terabytes of data, more than you can fit on your computer. So the software that we're writing has to be able to go through these images in real time as they're coming in off the telescope and figure out what has changed in these images, what is scientifically interesting, and what is just noise or garbage or calibration that needs to happen still. So the team here at the University of Washington, we're part of the larger data management team for the LSST, and we're specifically responsible for alert production, which is kind of the real-time analysis of the data as it comes in off the telescope. And one technique that we use to do this is called difference imaging, which is pretty much what it sounds like. You take one image of a certain region of the sky, and then you compare it by subtracting it, more or less, with another picture of the same region of the sky. So if there was a picture taken, say, a few months ago, and then you revisit that same area and take another picture of the same thing, maybe a source or two got brighter or dimmer. And you can use that to figure out interesting things that may have happened in space. Maybe an asteroid was going by at one point, but not at another point. And this difference imaging technique is pretty straightforward in principle, but it's really powerful when you apply it to the huge amount of data that LSST is going to get. After we finish difference imaging, we're going to have a whole slew of sources that LSST has found in the course of a night. There's going to be something like 10 million interesting things that happen every night on average. And interesting things could be something changing in brightness, or something moving, or just something that's different from our reference point to what we just took. And so we're going to be issuing alerts out to the astronomical community at large, which is going to tell people, look, at this little chunk of sky, there's this interesting new thing that you might care about. And then people are going to have the opportunity to filter those alerts to find the science that they care about and publish amazing papers about it.
I'm Joachim Wuyens. I'm a graduate student at the University of Washington. I'm also a member of the DiRAC Institute. And I study the solar system. And in particular, I study asteroids. And my main area of interest is understanding how the detections of asteroids in astronomical surveys can be linked into predictable paths of motion across the sky. So in the area of ZTF and LSST, the main contribution of those two projects is just the sheer volume of data that they will generate. And what that means for the solar system is we will go from now knowing maybe 760,000 asteroids to knowing 6 million, if not more. And that's a completely transformative viewpoint to take on as a scientist. That allows you to study in much higher resolution the destruction and creation mechanisms in our solar system, how planets formed and how they might not have formed. Having knowledge of the spatial distribution of these asteroids and their chemical composition can also motivate and give insight into potential frontiers of exploration in the future. And so that's an extremely exciting aspect of having both these powerful telescopes and these astronomical surveys being online now or coming online in the future in case of LSST. Another exciting aspect about working at DiRAC in the area of ZTF and LSST is our collaboration with the B612 Foundation. And the B612 Foundation is a private nonprofit organization that is trying to essentially detect, to track, and to, if need be, deflect any potentially hazardous asteroids that we might discover in the area of these two new projects. And that's an exciting thing to be working on because the software that will do this is called what they call ADAM. It's the Asteroid Decision Analysis and Mapping software. And what makes the software unique is it'll be super robust. It's currently running on the cloud, and it gives the user, like you and I, access to this information. And that software is designed to inform us with regard to the decisions we might have to make with future potential impactors.
My name is Gwendolyn Edie, and I'm a postdoc here at the University of Washington in the Department of Astronomy. My postdoc is funded through the Moore, Sloan, and Washington Research Foundations, and I'm also a DiRAC postdoctoral fellow, which I'm very excited about. So my research interests are really in measuring the mass of the Milky Way, and one reason I'm interested in this is because of dark matter. So dark matter is one of the biggest mysteries in astronomy. We think it's pretty much everywhere in the universe, but we don't know what it is, and we haven't been able to figure out even what it's made of. So there's lots of evidence for dark matter in the universe. So one piece of evidence is that when we look at spiral galaxies and you look at how fast the visible material is rotating around the galaxy, it's rotating too fast in the outer regions for the galaxy to be held together by just the matter that we see. So the inference is that there must be some sort of dark matter that we can't see. Another piece of evidence is that when we look at clusters of galaxies, there also is not enough matter that we see to hold those clusters together. And so there must be some other form of matter that we can't see in the optical or X-ray or any other electromagnetic spectrum that is helping hold these clusters together. So those are two really big pieces of evidence. Another one is that when we try to make the universe in computer simulations, where we really start from first principles of physics, we can't recreate the structure in the universe that we see today unless we include dark matter in those simulations. So that's really big evidence that we probably need dark matter in the universe. Either that or we don't understand gravity. But up until now, there's been no theory for gravity that can explain all of the different pieces of evidence that we have for dark matter. Right, so measuring the mass of the Milky Way is not an easy problem. One reason is that we're actually in the Milky Way ourselves, so looking out from the inside out makes it kind of difficult. We can't just look at it externally. So that's a challenge. Another challenge is that how can we measure something we can't see, this dark matter? So one way of doing this is to look at objects that we can see and find their positions and their velocities, and then use those to infer something about their orbits, and that will tell us how much gravitational pull they're feeling. And that gravitational pull is related to how much mass there is. So if we can figure out how much total mass there is and then subtract out how much mass there is from the luminous matter, then we can figure out and infer how much dark matter there is. So there's lots of different objects that we can use to measure the mass of the Milky Way. One that I like to use they're called globular clusters. And globular clusters are these really dense spherical objects full of tens to hundreds of thousands of stars. And they're very, very compact and they're very old, and they orbit around the Milky Way. And these objects, even though they have hundreds of thousands of stars, they can be treated as point objects in relation to the really large galaxy. So by looking at their positions and their velocities, we can figure out how much dark matter there is using their orbits. The challenge with using these objects, however, is that up until recently, we haven't had the full motion measurements for these clusters. So most recently, the Gaia data release came out just last week, so I think it was April 25th. And now we have proper motion measurements for not just these globular clusters, but for 1.7 billion stars in the Milky Way. So I'm really looking forward to using this big data to get a better constraint on the mass estimate of the Milky Way.
My name is Daniela Putin, and I'm the Associate Director for DiRAC. My research mostly focuses on one major question, and that question is, how do we convert data into knowledge? How do we take all of the new data that we're collecting with all of the new shiny big telescopes and convert it into knowledge about our universe, physics and astronomy, and knowledge about celestial sources? There are basically three parts how I try to do that research. The first is I try to do astronomy with time series, so I look at the brightness of stars and other sources over time, and then I analyze these time series and try to learn something about the underlying physics. But you can't really do that without having good software tools to do the actual data analysis. So I also write software in order to do that data analysis. the third thing that I'm really concerned with is how to build communities, and in particular, how to teach data science to astronomers and how to build a community of data scientists within astronomy, both within DiRAC as an institute, but also in the sort of larger field. As you might know, DiRAC has 4 themes. DiRAC is grouped around 4 big research areas. There's the solar system group, which works on asteroids and other solar system objects and the physics of those types of sources. There is the time domain group, which I am leading, where we look at how the brightness of sources changes with time and how we can use that in order to derive some physics out of this. There is an infrastructure group, which works mostly on scaling up algorithms and databases to the new large data sets that we're collecting, and how to take all the algorithms we're developing in the time domain group and the solar system group and put them on sort of large architectures. And then there's the LSST group, which is actively building the Large Synoptic Survey Telescope, one of the big future telescopes. Today, I want to talk to you about one specific research topic, research project that we've been working on within 2 of those groups. One thing that we actively try to do within DiRAC is not just work on one thing. Our themes are really themes, they're not closed groups. Many of us move between those different themes. And so one thing that happened last year was that the solar system had an interstellar visitor. Last year we detected the first interstellar asteroid to ever come into our solar system that we could measure, and that asteroid sort of went around the sun and then slingshotted back out of the solar system, and there was a very narrow time period of a month or so where we could see it with telescopes and actually try to learn something about what that asteroid is made of and where it came from. And that was a really exciting opportunity because that was our first opportunity that we knew about to actually study a rocky body from outside our own solar system in that much detail. So a lot of people, a lot of groups went and took observations, our solar system group among them, but then some of them came to me and said, we have these time series where we looked at the brightness of that asteroid over time, and that's really how we get all of the information out of this data set, but we don't really know how to analyze it. Do you have a better way? And so we put together our knowledge from the time domain group, all the algorithm knowledge that we have in that part of DiRAC, and the physics knowledge in the solar system group, and worked together to analyze this data. And what we found was that if we applied new methods that had never been applied to this data set before, we could get actually a lot better results out of it with less data than some of the other groups similar research. And what we found is that this asteroid is very, very, very elongated, which we didn't expect, and that it doesn't rotate on a sort of nice, regular rotation, but it's tumbling through space. And so those 2 measurements have implications for what we can tell about the structure and the composition of this asteroid. This project is exemplary of the kind of work we want to do in DiRAC, where we put together different people and different groups with different expertise and get them to work together on things to do entirely new projects and new approaches to data analysis and to how to do astronomy. We're really excited about is our DiRAC Summer Fellows Program. For the DiRAC Summer Fellows Program, we're going to invite a cohort of graduate students who will apply to a competitive fellowship and have them come here over the summer for 3 months. And each of them we're going to pair up with one of the DiRAC researchers who's an expert in some topic related to data-intensive astronomy or data science in astronomy. And we're going to have these graduate students work with DiRAC researchers very intensively on projects related to data science and astronomy and do cutting-edge research in that field. So I'm hoping you will join us in making this possible.